3 unsolved problems in this field right now. 1. Your model has a 200,000 token context window and it still forgets what happened in the middle of the document. 2. Your model speaks English magnificently and cannot handle Yoruba, Quechua, or Bicol at anywhere near the same quality. 3. Nobody, including the labs that built these models, can point to a specific neuron and say this one learns metaphor. We are shipping trillions of parameters we do not understand. Welcome back to Lecture 10, Video 8 of 10. Today, an honest tour of where the frontier actually is. Not hype, not doom. 3 specific technical problems that people who work in this field think about every day: long context reasoning, low resource languages, and interpretability. 7 covered how we align models. But alignment assumes you have a model that works well enough to align. This video is about where models still fall down. And the reason to know the open problems is not just academic. If you are a practitioner picking a tool, you want to know its actual limits. If you are a researcher choosing a topic, you want to know where the real questions are. These 3 are the ones I would bet on. Today's puzzle. Each of these 3 problems has attracted enormous amounts of engineering effort and money. Each one has visible headlines announcing progress. And each one is still, in a fundamental sense, unsolved. Why? Because they all point at limitations of the architecture that runs the field, the transformer. Each open problem is a place where the transformer's basic assumptions break down. Today's 3 beats. First, long context reasoning. 2 million token windows sound impressive. Then you test them and find out about lost in the middle. Second, low resource languages. 7,000 languages exist. GPT-4 works well in maybe 40. The other 6,000 plus are quietly left behind. Third, interpretability. Sparse autoencoders, monosemanticity, circuits, the quiet corner of the field trying to understand what these models are actually doing. Beat 1. Long context reasoning. In 2017, Vaswani gave us the transformer. The attention mechanism is quadratic in sequence length. A 1,000 token sequence needs a million pairwise attention scores. A 1 million token sequence needs a trillion. That is the cost model that shaped the field for 6 years. Every recent LLM has pushed against it. GPT-4 Turbo at 128K, Claude at 200K, Gemini claiming 2 million. Longer context is genuinely useful. It has also revealed a hidden failure. Liu and co-authors, Stanford 2024. Lost in the middle. They inserted a single answerable fact into a long document at different positions. Beginning of the doc, the model found it. End of the doc, the model found it. Middle of the doc, the model forgot it. Even on models advertised as having reliable long context reasoning, the U-shaped attention curve was the same regardless of context window size. Buying more window does not fix the shape. Various fixes are being tried. Ring attention. State space models like Mamba. Better positional encodings. Retrieval on top of long context. Every fix moves the needle. None fully solves the problem. Long context reasoning is where the theoretical assumptions of the transformer start creaking. And there is a strong argument that solving it properly will require an architecture change, not just a longer window. Which is why alternative architectures keep getting research attention. Beat 2. Low resource languages. About 7,000 languages exist in the world. GPT-4 handles maybe 40 at production quality. Every other language sits somewhere on a scale from usable but rough to basically doesn't work. Joshi and co-authors, ACL 2020, in a paper called The State and Fate of Linguistic Diversity and Inclusion in the NLP World, put this on the record. They classified languages into 6 tiers by resource availability. Tier 5 is English, Chinese, Spanish. Tier 0 is basically abandoned. Why is this hard? 2 reasons. 1. Internet text is heavily concentrated in a small number of languages. English alone is around 45% of common web crawls. If your pre-training data is 95% 100 languages, your model will speak those and struggle with the rest. 2. Many low-resource languages have grammatical structures, agglutinative morphology, tonal semantics, evidentiality markers that the tokenizer and architecture were never designed for. There is real progress. Aya at Cohere covers 101 languages. NLP from Meta translates 200 languages. Community efforts like Masakhane build tools for African languages from the ground up. But every one of these projects reports the same shape. The top 40 languages work, the middle several hundred are mediocre, the tail thousands are still barely served. Fixing this properly is a data problem, a compute problem, an evaluation problem, and a linguistic expertise problem simultaneously. Beat 3. Interpretability. If you crack open a 100 billion parameter neural network, what do you see? Historically, soup, a weight matrix, a ReLU, another weight matrix. You can compute what the network does, but not why. That started to change around 2020 when Chris Olah and others at OpenAI, then later at Anthropic, began publishing papers under the umbrella of a mechanistic interpretability. The premise: networks contain identifiable circuits that do specific things, and we can find them. The biggest recent result: Anthropic's 2024 Scaling Monosemanticity paper. Using sparse autoencoders, they extracted features from Claude that fired reliably for specific concepts. A feature for the Golden Gate Bridge. A feature for code that looks vulnerable to SQL injection. A feature for someone hedging in a diplomatic tone. Not just one or two, millions of them. Which means the polysemantic soup can, at least in principle, be teased apart into a legible vocabulary of concepts the network is thinking with. But, and this is important, even the labs doing interpretability will tell you they are nowhere near a complete map. Modern SAEs recover a subset of features. Circuits research explains a subset of behaviors. The gap between we found one interesting mechanism and we understand this model is enormous. Interpretability is the frontier where honesty matters most. Because if you cannot see inside the system you deployed, you also cannot really promise it will not surprise you. That is the current situation. 3 takeaways before the quiz. 1. Long context reasoning. Windows have grown to 2 million tokens. LU 2024 lost in the middle shows they still forget the middle. Buying window does not fix the shape. 2. Low resource languages. About 7,000 exist. Roughly 40 work well. Joshi 2020 laid out the 6 tiers. Aya, NLP, and Masakhane make progress, but not parity. 3. Interpretability. Mechanistic interpretability. Sparse autoencoders. Anthropic 2024. Scaling monosemanticity recovered millions of readable features. We still cannot see most of the model. Quiz 1. What did LU 2024? Lost in the middle demonstrate about long context LLMs. A longer context always improves accuracy uniformly. B. When a target fact is placed at different positions in a long document, recall accuracy forms a U-shape, high at start and end, low in the middle, regardless of how long the context window is. C. Only Gemini can handle long contexts. Or D. Attention is not quadratic anymore. B. The U-shaped failure. Beginning and end are found reliably. Middle is forgotten. Adding more window tokens does not straighten the U out. It is a structural attention problem, not a capacity problem. Quiz 2. What did Joshi 2020 State and Fate of Linguistic Diversity put on the record about NLP? A. That all 7,000 world languages are well supported. B. That languages classify into 6 tiers of NLP resource availability. A small set English, Chinese, Spanish is tier 5 and dominates, while thousands of tail languages are effectively abandoned by the field. C. That English is the only language worth studying. Or D. That machine translation is solved. B. The 6-tier framework and the growing gap. Roughly 40 languages work at production quality. About 7,000 exist. Aya, NLP, and Masakhane are pushing on it. Not there yet. Quiz 3. What did Anthropic's 2024 Scaling Monosemanticity paper demonstrate about interpretability? A. That neural networks are impossible to interpret. B. Sparse autoencoders can extract millions of individually interpretable features from a production LLM Claude, suggesting the polysemantic weight soup can, in principle, be teased into a legible vocabulary. But we are still far from a complete map. C. That Claude has 12 neurons total. Or D. That only rule-based systems are interpretable. B. Golden Gate Bridge features, SQL injection features, diplomatic hedging features, real progress. And still, the interpreted region is a small corner of the total model. The rest is dark. Back to the puzzle. Each of the 3 open problems is a place where the transformer's assumptions break. Attention is quadratic. Data is English-heavy. Weights are polysemantic. Every fix is a partial fix. That is not a discouraging picture. It is where the actual work is. Next video, the big one. Do LLMs actually understand anything? Next time, the biggest question in the field. Do LLMs actually understand language or just imitate understanding? Bender's octopus, stochastic parrots, Piantadosi's counterargument, the puzzle we have been running the whole course. Hit subscribe.